operations. And there are other things. There's topology, which is closely related but very, very much more abstract than analysis, because you don't just deal with real numbers, you deal with other kinds of things. So, okay, but now we're done with our axioms for R, and we'll prove what we are able to prove in this class, and and just at this point trust that everything else can be worked out and has been worked out, at least for what you've already used. This also was not understood until the 19th century, by the way. So it was a couple thousand years before people, between when people said, wait a minute, there's not enough rational numbers, to finding out exactly how to do it so that you could actually prove all the things, that, for example, Newton figured out and Leibniz well, decades, centuries before, right, was finally worked out properly with this kind of definition. Okay. So let's prove a couple of things about this, and these are the kinds of things that you're going to have in your homework. And again, it's often in mathematics, and if you're a math major and going on further, and you'll discover that when you take a class in a new subject, and here it's kind of like what we're doing. We're having a little new mini class every time, or course every time we get a new axiom or something, right? It will take you some time to get used to the methods and the ideas behind it, right? So you will have to work at it, work the exercises. And I'm giving you this, a lot of you are math majors or math minors, and I'm giving you this advice for your later classes. First of all, don't panic, right? If things don't make sense instantly. Maybe they used to when you did calculus. I mean, maybe you're one of the lucky ones where, oh yeah, the teacher writes down something from calculus, and yeah, I can do that, that's great, okay? Things become less and less instantly comprehensible the farther along you get, okay? Until you have to work really, really hard, like I do, to try to understand a new concept. And the things that you can understand quickly will also, right, increase in complexity, right? I mean, hopefully 2 years from now you see stuff at this level, it's like, oh, okay, right? So no problem, right? And so that's the goal here, is to sort of toughen you up and get used to more complex things. But just remember that it's going to be hard and complicated, and maybe you won't even get it at first, right? And you're going to have to work to get it. And that's partly what you're learning in here. You're learning how to learn mathematics and what it means to understand it. So you shouldn't feel right until you actually really understand it. And a lot of you don't quite have that sense yet. And that's what you're supposed to get. Okay, so we're going to do some things here, and the idea here is not, the actual things I'm proving are useful for you, but the idea is to get you used to what we're doing so that you can do proofs yourself. So let's do the first one. Suppose A and B are subsets of R. So when we say that, you should think, okay, when I write down R, that means I've got the completeness axiom to work with, okay? So I have existence of any soup. A is not equal to the empty set. A is a subset of B. And B is bounded above. Let's see, actually, I think I didn't use this wording earlier. Bounded above means that it has an upper bound. Okay, so the situation is, see, we're in R, right? We don't know much about R yet, but we do know that it's a complete ordered field. That's pretty much all we know about it. So here's B. And again, this may not be an interval. A and B could be all commingled in together, right? It may be very difficult to figure them out. Okay, you certainly don't have the situation where, the simple-minded thing where you have A here and B here, okay? Okay, so here's my picture. But what's the first thing that you ought to be able to conclude? I mean, what's one thing you know about B, first of all? Well, yeah, you're given that, but what's the other thing you know about B from what's written down about A? It's non-empty, okay? And it's bounded above. Since B is non-empty and bounded above, what do you know about it? Has a supremum, okay? And so we'll put this right here. B. B has a supremum. Okay, but it's also bounded above. So if I put an upper bound in this picture, right, that's an upper bound. It may not be the sup, it is some upper bound, but since it's an upper bound, I do have to put it to the right of the sup, right? Or equal to the sup. Okay, so from this picture, what can you tell about the relationship between A and M? Well, let's forget supremum because we can't even talk about the supremum of A until we know what?
M would be an upper bound.
Yeah, so from this picture it seems clear that M should also, every upper bound of B should be an upper bound of A, right? Okay, so that's the first thing we want to, if M is an upper bound of B, then M is an upper bound of A. Okay, so assuming we've done that, then we know that A is bounded above, right?
Yeah.
So what exists? Supremum of A. And what should be the relationship between the sup of A and the sup of B? Yeah. Okay, this is something that should be totally obvious from the picture, but you know what I think about the word obvious. Okay? Let's prove it. So for the first thing, what are we going to do? It's an if-then statement, opening line. Suppose, well, let's start with M. Yeah, suppose M is an upper bound of B. What is it I want to do now? I want to show it's an upper bound of A. And so what's going to be my opening line now? Yeah, this is what I mentioned earlier, right? Your standard opening line to show that M is an upper bound of A is to let X be an element of A. What do I need to show? About X?
X is also
We want it?
contained in.
Well, you're doing the proof, but what's the last line that I want to show about this? X is less than or equal to M. Okay, so then I already heard the next line, right? Since A is a subset of B, what do we know about X? X is an element of B. And since M is an upper bound of B, what do we know?
X is less than.
X is less than or equal to M. Right? So by definition, M is an upper bound of A. Okay, so again, in terms of the picture, what did we do? We picked up an X. We said, well, X is in A, but A is a subset of B, so X is in B. M is an upper bound of B, and since X is in B, X is less than or equal to M, but that's what we wanted to show, to prove M is an upper bound. Okay? Questions about that? Okay, what about this next one? We could, but let's not. It's a little complicated. Well, to do this, I'm going to write down the two properties of a soup. Okay, I'm going to call them S1, and that is that soup A, S. First one is that S is an upper bound of A. And the second one is that for every upper bound M of A, what do we know? S is less than or equal to M. Okay, so it's very useful to remember these two properties when you're proving things about the supremum, and we'll use those quite a lot, especially next time. Okay, so if we're going to show that something, so if we want to show, this is why we're not doing proof by contradiction, because this is quicker, okay? So if we, and this is a very important strategy, to show that soup A is less than or equal to some number, let's just call it M, we need only prove what?
Those two properties are true?
Well, less than that, because we're not saying what this is. We're just trying to show it's less than or equal to something else. So what do we have to show about M? M is an upper bound of A. Okay, and this is really, really important strategy that you will use a lot, and it will save you a lot of time. Okay, does everybody see that? If I'm trying to show that the soup is less than or equal to something, if I show that something, whatever it's called, is an upper bound of A, I'm done. Okay, so let's translate that into what we're trying to prove here.
So, since we have that M is an upper bound of B, we have that.
Okay, but there's no M here yet.
Okay.
We're trying to show that the soup of A is less than or equal to this something. What do we need to show about the something?
Soup of B is in upper bound of A.
Right? Okay. Well, since soup B is an upper bound of what?
B.
Of B. Right? That's our S1. By what we just proved, what do we know?
M is a upper bound of B.
Yes, we just proved that if we have an upper bound of B, it's also an upper bound of A. Now, we're not dealing with M here anymore, right? We're dealing with soup B is our upper bound. So instead of M, or you can replace M in this statement here, right? And what do we get?
And the SB is an upper bound of A.
Yes, soup B is an upper bound of A, right? This is from what we just proved. If we know something is an upper bound of B, then it must also be an upper bound of A. Now what?
Soup A is less than or equal to.
Yeah, now we're done by our second property there. Now, if you preferred, you could rename soup B as M. Some of you were sort of mentally doing that, right? And then unravel that here, and you get soup A less than or equal to M equals soup B. But it's good to be able to think abstractly about this and not rename it exactly what it was in there, because if you do that, you'll go crazy eventually, right? Having to rename everything exactly the way it is in the theorem. But if you use the theorem 3 times in the same proof, you can't rename everything exactly the way it is in the theorem. Okay, so and again, this is one of those things, I'll warn you right now, some of you will say, yeah, I understand this, great. And then you will go home and you'll say, I don't understand this. Okay, and probably most of you had this happen before, and this is one of those situations where if it's going to happen, it's going to happen with this one, okay? So make sure you understand it, and understand it means when you go home and look at this, yeah, you really get it, okay? So that's it for today.